Hello everybody, and welcome to the next lecture in this course, which is going to be on machine vision in aircraft maintenance. Now this is quite an important area, of course, for aerospace operations, because we need to make sure that the maintenance is done to the correct standard to ensure the required continued airworthiness of an aircraft or the aircraft parts. So it could be inspecting the exterior fuselage or wings of the aircraft, or it could be looking at parts from the turbines or other parts on the aircraft. So we need overall, inspect it, replacement with certified parts, defect rectification, modifications, and of course compliance with airworthiness directives and repair. So you can see that this aircraft is coming from Iberia, it looks like, for inspection. And we've got the turbine on a trolley here, and we're doing a full inspection of the engine there, by the looks of it. This is a very important area, repair particularly, for example, of aircraft, is done to the correct standard, because if it isn't, unfortunately, it can have bad consequences. There are quite a few examples you can find on the internet and so on, of where the exact procedures weren't followed. For example, it could be something simple like repairing damage to the fuselage or tailplane, where you don't use two sets of rivets, someone just uses one line of rivets, and that leads to a stress concentration, which can lead to serious things like the tail coming off and loss of the aircraft. So it's very, very important to follow the exact safety requirements on these procedures, standards. And of course, when we're looking at inspecting the fuselage, we could use something like a drone, which I mentioned before, and we can get a decent quantitative understanding of airframe condition. We can measure defects and the size of them, seriousness of them, to give us a complete ongoing record of what's happening to the aircraft. And you can see this aircraft has got a rather nasty dent in the front there. And things like bird impacts are more serious than people might imagine. Obviously, that's got to be replaced there. But high-speed bird impacts can damage the fuselage and, of course, also damage the engines. And in fact, a company like Rolls-Royce will, at some point during the development of an engine, a turbine, will start typically running it up to full power and throwing chickens into it and so on at some rate to try to see how it can handle that kind of those kind of impacts. Dead chickens, I may add. But that's the kind of thing that aircraft engine manufacturers do. And a lot of serious crashes have been caused by birds at near airports, of course. There was one in New York not that long ago. Well, some years ago, but these things quite regularly happen. Of course, you could put a grid on front of the engine, some sort of a mesh or something. But the problem with that is that would lead to such drag over the whole use of the aircraft that the chances of a bird impact are pretty low. So you might be better off just monitoring the position of the birds by radar or something, and then trying to avoid them that way. But anyway, you can get certain damage from various things. Of course, weather, hail and so on could also produce quite a lot of damage, which we'll talk about. Bird strikes, even lightning strikes. We've got to make sure that any damage we got, like dents, is still within the allowable tolerance limit for the aircraft to continue flying until the next scheduled maintenance cycle, of course. And the traditional way of measuring something like dent damage would typically be just to use, like in that case, a dial test indicator we've got here. And but nowadays we can move on to more easy, more comprehensive measurements using a 3D optical metrology. So we don't necessarily need to dial tests. We can just use an optical system which can give us a bigger coverage rather than just measuring, the dent size in one exact point. And probably get more objective results, where we don't get different results depending on who's done it, because people tend to measure in a slightly different way and so on. A bit more reliability. That's what you want, of course, for a system where you're trying to measure these things continuously. And we have 3D optical metrology equipment, and which these people here are using. As you can see, typically with these kind of systems, you normally got a projector and a camera, and you're probably using triangulation to work out the position in the field of view, with probably reasonable accuracy. Triangulation is quite an accurate approach. So probably also you're covering a reasonable area, which of course, if you've got an aircraft, you might have damage extending over some quite large area. So having an ability to measure exact depth over an area is certainly a plus. But even so, doing what these guys are doing, although it's precise and non-contacted, it's got disadvantages such as being a bit time-consuming to go around like that in that way. And of course, the guide needs a certain amount of skill to actually implement these measurements in a repeatable way. So the alternative is where we have a situation where we don't want the user to necessarily have skills like programming or data processing skills. We just want them to come in and push a button to set off the automatic inspection. So we want it self-enclosed, as it says there, and real-time analysis. And we want a handheld portable system, and we want it transferring seamlessly from the workshop to the hangar. So we're talking here about a very accessible, easy to use, very objective, repeatable system, which will be automated and quick to operate, and will give you the information integrated into your system, your maintenance system, in as quickly as possible, so you can keep an ongoing record of what's going on. And you could probably apply things like statistical process control methods, which you might be familiar with, such as control charts, which is quite an interesting way of monitoring damage that's occurring on aircraft. If you notice some damage at a certain point, you could continue monitoring it and seeing whether it's getting worse, whether it's moving up the control chart. Control chart has got the time on the x-axis and size of the defect on the y-axis, and and then control limits to where acceptable damage limits are. And you can even do a thing called a CUSUM chart, where you accumulate the damage, and it's very good at showing you trends that are occurring in measurements. So that's a whole area of statistical process control. It's one I've got some experience in. It's quite interesting because if you're getting this data, then you can want to make use of it in the best way you can, really, through statistics, for example. And as I say, triangulation then with these devices, you can see this is like a schematic, is how it's operating. You typically use a projector to project a pattern of lines, usually linear sort of parallel lines. And you get a sequence of these lines, and any defects or damage or dents or whatever in the surface will appear as distortions in the position of these lines. And so if you've got the projector projecting these lines onto the surface of the aircraft, and the camera is also built in there, you see, there's a camera there, built in and capturing the image, then you triangulate in that situation, and you get, as I say, triangulation with the fringes, you get pretty good topology. In this case, we've got a little dent by the looks of it there, and they're showing false color to indicate the depth of this dent, and so it looks it's going from light here to darker as it's showing you clearly what the extent of the damage is really there. So real-time aircraft body analysis then. We've got these portable devices in the workshop at Hanging and you can complement it with augmented reality. And I don't know if you know what augmented reality is, but companies like Rolls-Royce use augmented reality quite a lot. And it's really something like you could be wearing a pair of special glasses, and they would be projecting into your field of view certain information, for example, and that would be giving you, it'd be like you could access a manual for the aircraft or instructions for how to inspect the aircraft. It could tell you where you are at each stage, and then you could be updating things digitally as you go. So it's projecting the information and it could even be showing you in your field of view where to put the device and helping you actually do the inspection. So it's sort of superimposing this augmented reality on the image you're getting, really. So it's not like virtual reality, it's not quite as far removed, but it's a lot easier for an operator to do that than it is for them to put everything down and start looking through a paper book, really. So that's the future of instruction for these guys doing this, really. And as it says there, helps with real-time analysis, driving efficiency gains, and I think it's more productive and enjoyable for the operator, really, to get their performance optimized in that way. Yeah, case studies in maintenance and engineering for EasyJet are illustrating the benefits we can get with these kind of techniques. And So in a self-contained design with zero learning curve, okay, we witnessed more than 90% improvement in the time taken to map and report dent damage. I mean, 90% improvement, that's pretty dramatic. And it's showing the different improvements in terms of the dramatic reduction in time from the blue traditional methods to the sort of orange with the new vision tools. And you can see it's a dramatic decrease in all these different areas to do with the inspection. And, the people trying to sell these systems like DentCheck are obviously trying to accentuate the positive angle on the way they perceive it. But I do think there are genuine benefits to be gained for using these kind of systems in comparison to old-fashioned manual techniques for inspecting damage. I mean, they say that EasyJet realised a more than 80% time savings, disruption dents. I mean, the thing is, that's very crucial, especially for a company like EasyJet, because these aircraft carriers, airlines, are very highly geared towards, I mean, they have aircraft and they need a continuous source of income to pay off against the aircraft. So you can make big losses if you've got your aircraft out of operation for any extended time. That's why Boeing's having such a hard time with the 737 MAX, because it's been out of use such a long time. But they want to, if they've got the aircraft out for inspection, EasyJet, say a new A319, they want to inspect it and get it back into operation as fast as they can. So these kind of things could really be helping them with their efficiency of their operations. Now, Rolls-Royce, this is something we have a bit of experience of, working with Rolls-Royce, and they need to read the part codes on the turbines, of course. And some of these codes are a little bit difficult to read. I can vouch for this from experience because I was talking to them, trying to help them with this, and they brought in about 10 or 20 example pieces. And they sort of have an ultrasonic wand or pen that they use to writing numbers sort of onto parts, serial numbers or identification numbers. In other words, hand-etched codes. And what they were looking for is some machine vision technology would automatically help them recover and interpret handheld codes. In fact, this is the kind of thing that 3D vision, I mean, in our lab we've got two areas, 3D vision and deep learning, or CNNs, convolutional neural networks. And this is an example, I think, of where these techniques are pretty well suited to this kind of industrial problem. So when you use your etching or your stamping especially on a part to put numbers and alphanumeric information on there, you've got a three-dimensional profile to some extent. So we can use some of these three-dimensional high-resolution techniques we've got to actually recover that. So even if there's marking or pigment or whatever's happened, or debris, a certain amount of coloration on a part, we can still see the 3D marking on there because we can remove, with our techniques, the 2D pigment from the 3D shape or texture. And then, of course, I think also neural networks and particularly deep learning come into this because, I mean, the first really successful application for deep learning, or convolutional neural networks, was really Yann LeCun, this French guy, who developed it for reading text off checks. So he's really thought of as the first guy who had a successful convolutional neural network. And, that's still being used. So that goes to show how useful these kind of deep learning techniques are for text recognition. So that's what Rolls were interested in. But just going back to that, I'll make one more comment maybe before leaving that. And that's that, to be honest though, if you just had standard stamps being used, or standard etching or whatever, to put these alphanumeric codes onto this part, you'd make life a lot easier. You don't want to involve complexity in industrial operations or non-standard, industrial operations, if you can avoid it. So if you've got different guys using the hand etching tool and writing things on a different way, you're introducing loads of potential complexity, which you ought to really avoid. Because if you could just have standard ways of noting marks onto turbine parts, then you could probably use optical character recognition to just read them off, for example. So it's just a case of keeping things standard as much as possible. Anyway, talking about the centre of machine vision, and as I was saying a minute ago, we've got this expertise in 3D imaging, known as photometric stereo, which I'm going to talk about a few times, and that's what we applied actually to the turbine parts. And we got this 20 years experience in developing real-world functional prototypes for companies all over the world actually. And a lot of the time we're needing high-speed applications, or at least high precision applications. This is a typical industrial camera we might employ, you know, with a, you can see it's got a metal case and you've got a standard sensor there. This is a C-mount lens, so there's different ways of mounting the lens onto the camera, and you want to make sure that you get a lens which is suited to the sensor you've got. There's no point in having a huge sensor and a small lens. It wouldn't make any sense because you wouldn't get a decent, you'd get a variation in brightness across the image, for example. So the lens is actually very important. That's something not to be underestimated. So you usually spend £400 or £500 just on the lens, you know, for any given application. And it may be that we are doing we're doing prototyping in the lab. We're trying to get things working. Once we work out what does work, then we can start worrying about cheaper lenses or how to, you know, the company can look towards reducing the cost of the lens by using more standard components or less flexibility or just cheaper type lenses. Once we've got it working, we can start reducing costs. But we want to get the quality up to make sure we've got the right solution. And, you know, as I say, Rolls sent us these turbine parts, and I started using them with a thing we got called the skin analyzer, which we've been developing over the last 18 years. And this device, which is the one that the version that Abdul designed, there's been about 4 different versions of this so far. This is Mark III. You can see it's got a set of lights built in here in known positions, and it's got this camera in the middle. And again, it's using the technique photometric stereo. You can sort of use this part of the device to rest against whatever surface you're trying to recover. And it flashes these lights in less than half a second, very quickly. And you get a nice quality data from this particular version of the device. And the important thing is that you can recover and separate 3D from 2D textures at very high resolution. You know, for this one, about 20 microns, which really is useful in lots of different applications. We use it with 1,000 patients at the hospital, and I'll go into that more in a future lecture, but we've also tried to use it on these aerospace parts and the way it's working is that we've got 6 lights, 2 sets of 3, to recover the 3D texture, which we call the bump map, and 2D texture, which we call the albedo, it's like the pigment, from surfaces. In the case of the bump map, each pixel location is replaced by a vector. There's a surface normal at that point. So, you know, here's our light here. Sorry, here are our lights, 3 of them in this case, and here's a camera, and we've got a lighting model. Now, with this, this is rather a busy slide, but it does show what we've got. So we've got the original surface here, then we're using the technique to separate the surface orientation at each point, which we call the bump map, from the surface pigment, which we call the albedo. In fact, you don't need these arrows on here. We could have probably done away with them. We're just showing the color here at each point. And then what we've got in reality, of course, is a surface which has different colors at different points and different surface orientations. We're just extracting the information that we want to analyze at any given time. It works remarkably well. It's quite a robust technique. We've got 6 lights in this setup to build in what we call redundancy, because this technique, as I say, works with a minimum of 3 lights. But if we put 6 in, then even if we've got some sort of highlighting from the surface, which causes a problem for the system, we can just use a different combination of 3 lights. So this, to avoid problems like that, we call them image artifacts. To avoid those, we use the combination of 6 lights. And also, we had a researcher who developed the first skin analyzer with me about 18 years ago, who discovered that for any convex surface, you can fully recover it with this technique using a minimum of 6 lights, which I thought was quite an interesting development. Anyway, so we have in this case here, we have a tile. I think it was from a swimming bath, this one. And it has a sort of texture in the slip. And then it has also the 3D texture in the molding of the tile. And with our technique, we separate it into, there's a slip, the 2D texture, and there's the 3D texture of the molding. This is quite important for tile manufacturers, because they want to know, for a tile, when they're making these tiles, if there's a problem, whether it's got to do with the printing or the slip operation, whether it's got to do with the molding operation. So if there's a problem, they can go and address it at the right position in the manufacturing operation. So Abdul developed this. He did his PhD on developing this for a company in Bristol who were actually manufacturing machines to inspect tiles. Yeah, so that was quite a nice project. And the next thing we can do, once we've recovered the surface, is we can analyze it in 2D and 3D. I've got rather a lot of text on this slide, but As it says, virtual light sources can then be used to visualize the bump map in the form of the rendered surface. We've shown that on the next slide. And this is, in this case, 3D punched text. Now, the 3D nature of the lettering is clearly defined, and the texture of the metal surface is also recovered. True grey horizontal lines were in fact areas of black paint. You'll see this in a second. The bump map does not contain any pigment information. No texture is visible in the painted areas, indicating that it's smoother than the metal areas. A line can be seen going from the 6, passing through the 1 and continuing above the M. It's in fact a scratch, as you can hardly see this. When I was looking at the part, I couldn't really see this scratch. But you can see it with the data from the skin analyzer. So when we visualize the 3D data, we've got the bump map in computer memory, and then we have a virtual light in the computer, and we alter the position of the virtual light. And we apply what we call the lighting model, which is Lambert's law, which I talk about in other lectures. And that allows us to look at, it looks as though we're looking at the 3D part, it's really the bump map we're looking at. And we move the light around to help us accentuate, identify certain 3D features, which might be quite important. So that's what I mean when I'm saying, visualize the bump map in the form of the rendered surface. Anyway, let's have a look at this. So this is, and we've got this device which is good for down to 20 microns. This is a scratch I was talking about, which looks quite large here, but it was actually pretty microscopic when you're looking at the part. This is a painted surface, which is actually smoother. You can see this is also just a relatively smooth metallic surface, you'd think, but you can see here we've got the 3D punched characters, and you can see that the virtual light in this case is probably off here to the top right, because we're getting a shadow apparently cast, or at least it looks like a shadow. And we're getting some brighter stuff here, as though that's the area which is more, the light striking more. So that's my Euro EJ200 engine, and we're getting pretty good high resolution. We're getting this scratch information. So what we can differentiate here between marking and 3D, see, this is more likely to be just where the paint scratched off here. And you can even see the texture of the metal below, just about here. Whereas over here, as I say, the light is shining brighter off the lower surface, or the surface more to the left of this groove. And this is helping us identify this is a groove in the metal, but this just being a scratch in the paint. And again, the groove continues here, and you can see that again. So it's giving you what we call rich data. It's giving you lots of 3D data, which is allowing you to work things out about the surface. I think by doing a texture analysis in 2D on the 3D data here from the part surface, turbine blade surface, you could probably get a reasonable estimate of the actual surface roughness, or RA value. That would be a quicker and easy way. I mean, with conventional RA measurement, you'd have a little probe or stylus that you run across the surface, and that just checks just where you happen to put the stylus. But with this kind of technique, you could analyze texture over wide areas of the part, which might have a lot of benefits. And we also got 3D surface data from a weld on the turbine blade, which is shown in the next slide. And you can clearly see the morphology of the weld. And there's also a nice difference in surface texture visible on either side of the weld. And this isn't the sort of thing you can see very clearly with the human eye. And very fine cracks might show up quite nicely, I think, using this technique, especially versus very faint marking, because, again, the crack would have two surfaces, and you probably get light reflectors off those surfaces, and you get that more information. So differentiating between a fine crack and just a sort of very light mark would be very worthwhile for something like a turbine blade, of course. Or turbine part. This is the weld. You can see it showing up quite nicely. And then there's a surface over here which has some kind of 3D texture on it, which is quite clearly showing up. And here we got more like a random, this looks like it's got a certain pattern in it. But over here, because on this side of the weld, we're getting a more smooth surface, which has random but finer kind of texture on it, with also one or two little tiny marks, probably speckles from the bits coming off the weld, hot debris from the weld. And I'm sure you could inspect weld profiles and boundaries with this technique to try to see if there's any weak spots indicated. Because manufacturing defects in turbines do occasionally bring aircraft down, and sometimes they're inspected with ultrasonics or eddy current inspection equipment, but occasionally you can't do that, and you might be able to use vision. And there was this famous case of a DC-10, which the turbine exploded on the rear engine on the turbine, which is at the middle on the tailplane, and it cut through the hydraulics, and they completely lost control of the aircraft, which is an example of how if that had been inspected during manufacture, a lot of things would have been a lot better and a lot less chance of having a rather serious crash, in fact. So there we go on that. Now we applied the technique to the turbine blades, and we were able to identify the three-dimensional punched, in this case dot punched codes on a turbine blade, which is obviously very critical because you take that turbine apart, you want to make sure you put it back in exactly the same order as you took it apart. So you do need to take a close note of these serial numbers or production numbers. And that's just a typical, what it looked like, that was what it looked like, just to the naked eye. And then you can see with this technique, we're able to capture and highlight these codes quite nicely. So we used optical character recognition after highlighting them with the photometric stereo technique. So as it says there, real-time part identification and tracking, assisting with quality assurance during turbine maintenance. And of course, that's assists with the logistics of turbine blade manufacture and storage, a critical process as that is. 3D vision there was useful, as I was saying, for analysing the weld morphologies and therefore quality, as well as assisting with detection of scratches and cracks and building up a debris within turbines, blades and turbines, which actually is quite serious because debris can build up on various parts of turbines, which is meant to be noticed or inspected during routine maintenance inspections using a borescope, which is like an endoscope, but for looking inside engines. And sometimes it's missed. I mean, Egypt Air had an example where they missed it, and it destroyed the engines, in fact, on an aircraft. And so if we can automate this as much as possible and use 3D techniques as well, we stand a better chance of avoiding missing defects like that. So that's a sort of introduction to where we can get to on inspection in aircraft maintenance. I hope I've given some ideas of what people typically do in aircraft situations in routine maintenance. Companies like EasyJet. I think I found a paper where EasyJet are using a drone for inspecting things like difficult to reach parts of the aircraft, like certain parts of the tailplane, which I will put onto Blackboard, and it's quite interesting that companies are now really going ahead with this. So they're doing all that kind of thing with drones and so on, and it's also improved health and safety, of course, if you can do things on the ground controlling a drone rather than having to go up in a cherry picker or whatever they were using before. There's less risk involved with routine maintenance. And then so going through the routine maintenance that companies are doing with all sorts of drones and standard measurement equipment like the triangulation equipment I showed. There's also moving on to more sort of research type techniques that we're researching in our lab, which typically use other techniques as well, like photometric stereo. And of course, it's not just that. There are other techniques that can be used, like binocular stereo and other time of flight even as well can be used to some extent. And there's a range of techniques that we use, and we specialize in developing these systems by closely controlling the lighting positions and the lighting configuration, and then recovering the 3D data directly as much as possible, which is a lot of the time useful because it's less dependent on lighting changes. Sometimes, if we use specific wavelengths of light, maybe in photometric stereo we use infrared light, then we're less susceptible sometimes to background light changes which occur all the time, of course. Especially for certain frequencies, okay? Because there are certain frequencies which are not visible much in natural background light, like I think 940 nanometers. So if we use those frequencies and we use filters on the camera matched to that, and we use LEDs of those frequencies, then we can remove the effects largely of changes in background light. We find that to be useful a lot of the time. So I hope that's useful, introduction to machine vision aircraft maintenance. I'll see you next time.